All right. So we are heading up to the next test, and I'm planning on it being a week from Wednesday, so that'll be the day before Halloween, which I guess is better than the day after Halloween. So that'll be the 30th of October, and it'll cover all of Chapter 11, 11.1 through 11.10. You've already gotten, today you need to turn in the homework assignment for homework number 8, and then you've gotten the homework number 9 already for this coming Friday, a week from today. And then I'm planning on Monday then handing out the take-home quiz and that last homework on those last 2 sections, and that'll be due on that Wednesday when you take the test. Okay. So that's the plan. So let's see how much we can get finished with this power series section today. So we're talking about power series. So in general, a power series centered at some number A is the summation from 0 to infinity of some coefficients times x minus a to the n power. And so if we just write a few of those terms, that's going to be C naught all by itself plus C1 times x minus a plus C2 times x minus a squared, and then it just goes on from there to infinity. Now notice if we plug in a for the x value, everything becomes 0 except for that very first term. So the power series when x equals a just equals that first term C naught right there. So any power series centered at the number a will always converge when x is equal to that number a.
How do you know if it's centered at a?
Because you see it centered at a number. You see it here, it's going to be in the form where you have parentheses x minus some number. So if that a were the number 2, x minus 2 in parentheses to the n power, it would be centered at 2. All right, that's the number. Okay. What we're going to do here is go through, the whole point of this section is to find out when these power series converge to a finite number and when they don't. So, and we're going to primarily be using the ratio test to do this. So we're not going to be jumping around to a whole lot of different tests. So let's just go through, look at the first example here, and basically we're asking for what values of x is the series summation n equal 1 to infinity, this one starts at 1, of x minus 3 raised to the n power, all divided by n. For what values of x is that a convergent power series? So we can see right here, Jenna, that this is a power series that's centered at 3, centered about 3. All right, so we're going to use the ratio test for this. Now, our an term is going to be what we have after the summation sign, x minus 3 raised to the n power divided by n. Okay, so with the ratio test, we look at the quotient of a sub n plus 1 over a sub n. So let me write, and we look at the absolute value. So let's look at this, a sub n plus 1 over a sub n absolute value. And so let's then write in what we have, and then we're initially going to be getting kind of an unwieldy looking thing, which will simplify rapidly, hopefully. So a sub n plus 1, instead of putting n, I put n plus 1. So this is going to be x minus 3 to the n plus 1 power all over n plus 1. And then that's divided by the an term, which is x minus 3 to the n power divided by n. So as we've seen before, we have a fraction divided by another fraction. So I take care of that by multiplying by the reciprocal of the bottom. So this becomes absolute value of x minus 3 to the n plus 1 power over n plus 1 times the reciprocal of the bottom, times n over absolute value of x minus 3 in parentheses raised to the n power. Notice here, since the n's are positive numbers, I didn't go on and put absolute value around the n plus 1 and the n because they're going to be positive anyway. All right, so let's simplify this. Notice now on the top we have n plus 1 is our exponent. On the bottom it's just n. So those will cancel out to where I just have an x minus 3 factor in the numerator. And then then we still have an n over n plus 1. So that's how that quotient simplifies to that result. All right, now, let's see here. So now what we do with the ratio test is we take the limit as n goes to infinity of that quotient. So the limit as n goes to infinity of the x minus 3 times n over n plus 1. Now, I've done this often enough that I don't think I have to start belaboring this. What is this particular expression going to go to as n goes to infinity? It's going to go to 1, all right? Divide every term by an n, and we're going to find out it goes to 1. Is everybody okay with that without me going through that process that I've gone through several times already? All right. So this limit then is still going to be that x minus 3 in parentheses times 1. All right. Now, remember, the question is, what values of x does this converge at? So let's recall with the ratio test, the series converges if that limit of that quotient as n goes to infinity, a sub n plus 1 over a sub n, if that limit is less than 1. That's what the ratio test tells us. So we've determined what that limit is. That limit is the absolute value of x minus 3. So therefore, the series converges where x minus 3 in absolute value is less than the number 1. Okay. Question on that. We found our limit. Our limit turns out to be absolute value of x minus 3. So now we want it to be less than 1 to find out where it converges. All right. So this then comes down to basic algebra, college algebra, intermediate algebra of solving this particular absolute value inequality, which may be some people's favorite part of algebra. And so what do we do here when we have an absolute value less than 1 or less than a number? How do we solve this? Yeah, okay. So this is actually what I would do with it. You get rid of the absolute value, so just put x minus 3. And this thing has to be squeezed between positive 1 and negative 1. So I make it what's called a compound inequality, where that x minus 3 expression has to be lay between the positive 1 and the negative 1. All right? All right, and then we want to find what particular values of x meet this inequality, so we have to isolate x in the middle then. And the way in this particular example to do that is to add 3 to all 3 parts. 3 in the middle, 3 on the left, and 3 on the right. So what we come up with then, minus 1 plus 3 is a negative 2, less than x, less than 1 plus 3 is 4. So when x is between negative 2 and positive 4, this series will converge. Oh, thanks. Thank you. Between 2 and 4, the series will converge. All right? All right. And, okay, what happens, what about the endpoints then? What happens when x is equal to 4 and x is equal to 2? What?
It's not equal. It's not like the line under.
I know, but I'm asking the question, will this series converge at either of those 2 endpoints? We know that in this area here, it converges. We know that. Okay. But what about at 4? What about at 2? Yeah.
I think I remember the ratio test. Doesn't it converge conditionally?
Will it converge conditionally? We don't know that. We need to test them. We actually need to test each of those 2 endpoint values back into our original series and see whether it meets some other test for converging or not. Okay, that's what we have to do. Because remember this, the ratio test gives us no information or it's inconclusive when that limit of the quotient as n goes to infinity, when it's exactly equal to 1. We don't know anything. And in this case, that limit was the absolute value of x minus 3 when that's exactly equal to 1. And of course, those are the two endpoint values of our interval here. That's at x equals 4 and at x equal to 2. So that test has not given us any information about what happens there. So as Tom suggested, what we have to do is plug each of those two values in and test them separately. Plug each endpoint value into the original series, and test for convergence. So we'll see how this works here. All right, so let's first of all let's look at the one endpoint, x equals 2. All right, so we're going to plug this into our series here. This was our original series right up here, x minus 3 to the n power. So I'm going to plug in 2 for the x. So I'm going to get the summation as n goes from 1 to infinity. Now I'm going to have 2 minus 3 in the parentheses. So 2 take away 3 is going to be minus 1 in the parentheses, raised to the nth power all over n. So that is the series now that I'm going to test. Does this thing converge or not? Now, what are our thoughts on what we might want to look at with this series, particular series, that has the minus 1 to the n power in it? Alternating series test. It goes from negative to positive, negative to positive. So we're going to want to look at, the first thing we want to look at is I'm just going to abbreviate it, AST, the alternating series test. All right. So what do we have to know for the alternating series test? First of all, we have to say, does 1 to the n decrease? It has to decrease. That's the other part of it. This is minus 1 to the n times 1 over n. That's how you can look at that series. So does 1 over n, does that decrease as n gets bigger? Yep, it sure does. So I'm going to say yep. And the other thing is, what we have to look at is as n gets bigger and bigger, does that thing have a limit of 0? And it does. So we have both of our conditions for the alternating series test. So I can say this. So per AST, the series converges at x equals 2. So one of our endpoints is good. So now we need to look at the other endpoint. And we're going to come to a different conclusion with the other endpoint. The other endpoint was, now check x equals 4. Okay, again, here's our original series up here, x minus 3 to the n power. So when we plug in 4 for the x, we're going to have 4 minus 3, which is a positive 1. So no matter what power I raise 1 to, I'm just going to end up with 1. So the series becomes the summation of 1 over n, as n goes from 1 to infinity. Now you guys should know by now that this series does what? Converge or diverge? It diverges. It's a p-series with p equal to 1. It diverges. P is equal to 1. So we know that x equals 4, the other endpoint is not where it converges. So therefore, I can conclude the series converges at, and I'm going to put it in interval notation. Okay, we knew it was from 2 to 4, but now I know that I can include the one endpoint 2 as part of my convergent area, so I'm going to put a bracket there. The other endpoint of 4, I need to put a parenthesis there because it doesn't converge at 4. So this would be my answer as far as what values of x does my series converge for. Okay? And this has a name, by the way. These values, this interval is called the interval of convergence. Interval of convergence. So that's the whole process with these. We're going to do the ratio test on the series, get some kind of interval, and then we have to test the endpoints. That's the general game plan. All right? Okay. We ready for another one then? All right. Here we're looking at the summation from n, this time n equals 0 to infinity, of n prime times x to the n. Now just to point out, this one is centered at 0, because it's really x minus 0 raised to a power. So it's centered at 0. Okay, so we want to know for what values of x does it converge? For what values of x does it converge? All right. So this time, right, and again, we're going to use the ratio test. All right. So our a sub n term is the n prime times the x to the n. And we're going to do the quotient and take the limit as n goes to infinity. So first of all, let's look at what the quotient is. A sub n plus 1 over a sub n, absolute value. Now here I can really take away the absolute value of, no, scratch that. So let's figure out what a sub n plus 1 is. Well, I plug in n plus 1 for n. So this is going to be n plus 1 in parentheses factorial times x raised to the n plus 1 power. Over a sub n is n factorial times x raised to the n power. Okay. And now let's simplify what we can simplify here. Now we know that n plus 1 factorial is n plus 1, whatever that number is, times the factorial of the number underneath it. So that's n plus 1 times n factorial. Now we have an n factorial in the denominator, so that can cancel out with my n factorial in the numerator. So what I'm left with then is just an n plus 1 in the numerator there. Now let's look at the x. In the numerator we have n plus 1. In the denominator we have the exponent of n. So I can subtract the two exponents, and I'm left with an x in the numerator. Now that one I need to put an absolute value on. The n plus 1, I don't have to put, it's always going to be positive. So that's my ratio. So now with the ratio test, I take the limit as that n goes to infinity. So we take the limit of n plus 1 in parentheses times the absolute value of x. And there's going to be two cases here involved. What happens if x were exactly equal to 0? What would my limit be in this case? It would be 0, yes. If x were equal to 0, all I would have is n plus 1 times 0 So I have two cases. If x is equal to 0, I just have the limit as n goes to infinity of n plus 1 times 0, and that's just going to be a 0. All right. Now, what happens if my x is not a 0 number? It could be any kind of small fraction, anything like that. What would this limit be then as that n that's n plus 1 keeps getting bigger and bigger? What's my limit going to be? It's going to be infinity, right. We can get that n large enough that this can go all the way up to infinity. So here, if x does not equal 0, the limit is infinity. Okay. All right. Now, this first limit, when x is equal to 0, we found that the limit was 0. Now, remember with the ratio test, if the limit is less than 1, then it converges. So therefore, by the ratio test, it converges at x equal to 0. But when x is not equal to 0, we get infinity, which is certainly way bigger than the number 1, and so it doesn't converge for any other x value, because the limit is bigger than 1. So by the ratio test, it diverges if x does not equal 0, any other number. So the question was, find the values of x for which this thing converges. Well, we found out there is only a single value of x that will give us a limit less than 1. So the answer is, only at 0 does this converge. Okay. Converges only at x equal to 0. Okay. So that's another example. So with our first example, we found some kind of little interval in which it converges. Now for this one, there aren't any endpoints to check. All we've got is a single number. If we know it converges there's no endpoints to check. All right, it's just that single number. And we found where we had an interval and we checked the endpoints. Now we're going to look at a third example here and get a different kind of answer for the values of x where it converges. So here's our third example. Here we're starting the summation from 0 to infinity of minus 1 raised to the n power times x to the 2n divided by, in parentheses, 2n, and then we're taking the factorial of 2n. Okay. So just kind of to remind what the factorial of 2n means, this means we start with 2n, and then we multiply it by the next number down by it, and then the next number down by that, the next number down by that, etc., all the way till we get to 1. That's what it means. All right, so we're going to do the ratio test again. So our an term is going to be minus 1 to the n power, x to the 2n, all over 2n in parentheses factorial. Okay, so we do the same kind of process. We look at the quotient. So let's look at a sub n plus 1 over a sub n. All right. And again, every place that there's an, for the top, every place there's an n, I replace it with n plus 1. So for starters, I'm going to get minus 1 raised to the n plus 1 power. And then you've got to be a little careful here. What's going to be my new exponent up here on top for the x? Yeah, 2n plus 2. Be careful with this. I've got 2n. I have to replace that n with n plus 1. but I'm multiplying it in front by a 2. So we have to be careful. I distribute and I get 2n plus 2, not 2n plus 1. So that new exponent up there is 2n plus 2. All right, and then this is all divided by 2 times, oh, now again, this is going to be 2 times n plus 1 again. So it's going to be 2n plus 2 in parentheses factorial. Because I have to multiply inside the parentheses 2 by n plus 1 to get 2n plus 2. So you do have to be careful with that. That's my top part. And then it all is divided by minus 1 to the n, x to the 2n over 2n parentheses factorial. All right. Now, the first thing I want to ask is this. We're looking at absolute value here. So when I proceed on here trying to figure out what this simplifies to, do I still have to be concerned about that minus 1 to the n plus 1 and minus 1 to the n?
The value, not really.
No, we don't have to. All those do is either multiply it by a plus 1 or a minus 1. But if we're looking at absolute value, that gets canceled out, because absolute value is always positive. So I can disregard those for the next step here, because I want to start making things look simpler. So now I'm just going to put on the top x to the 2n plus 2, and now that still has to be an absolute value over the bottom, 2n plus 2 factorial, divided by, again, that x to the 2n there, that has to be in absolute value, divided by the 2n parentheses factorial. All right. So we're dividing by a fraction, so I'm going to multiply by the reciprocal. So this becomes absolute value x to the 2n plus 2 over my 2n plus 2 factorial, and then flip the bottom part. So now I'm going to have 2n factorial on top, and on the bottom I'm going to have absolute value of x to the 2n. Okay. And as you do these problems, you're probably going to recognize right away that you're just going to be multiplying by the reciprocal of that denominator. So you're going to be doing that rather quickly rather than continue to write out that big, messy-looking thing there. Just do it, because you know you have to do that. Now a lot of things will cancel out here. Let's look at the x terms here. I have an exponent 2n plus 2 on top and 2n on the bottom. So what am I going to be left with when I subtract the bottom exponent from the top? Well, I got 2n plus 2, and I'm subtracting 2n from it. So, right, I end up with x squared. And that's going to remain, I want to keep that in that absolute value. All right. Now, what about, let's see, I've got the factorials here. Now, this 2n plus 2 factorial is 2n plus 2 times 2n plus 1, and then the rest of it is just the 2n in factorial, all right? So I can cancel out the 2n factorial, right? Because that's in the top and on the bottom. Here and here. And then I'm still left, though, with those two first terms of the factorial, 2n plus 2 times 2n plus 1. Okay. We okay with that factorial simplification? All right. Okay, so I've simplified this ratio as much as I can. There isn't anything further I can do with this. So now what I have to do is look at the limit as n goes to infinity of what I got here. So that's absolute value of x squared over 2n plus 2 times 2n plus 1. Okay, so the only place we have the n's are down in the denominator, and they keep getting bigger and bigger and bigger and bigger. So what's this limit have to be? Has to be 0. Okay, now we're doing the ratio test. 0 is certainly less than 1. We have no restriction here on our x values. No matter what our x value is, this ratio test will pass. It'll be less than 1. So this is true for all x values. Therefore, by the ratio test, this converges for all x values. It converges for all x values. So if we want to write this in interval notation, the way to write every x value is minus infinity to infinity. And again, there's no endpoints to check with infinity. All right. So we've come up with 3 cases. So are we okay with that case? Kind of, sort of. All right. So use that ratio test. We've come up with 3 different situations. And those are the 3 types of cases you can encounter. So let me sum up what these 3 cases are then. Okay. So, in summary, a power series can converge 1 over some finite interval. That was the first case. Over some finite interval. And in this case, we have to check the 2 endpoints. Check the 2 endpoints. Okay, that was the very first case we saw. Now, another possibility that can happen is that's with the second case, where it only converges at a single value. Only at a single value. A single x value. Okay. And then the third case was the case where it converges over all values of x. Over all values of x. And that's the minus infinity to infinity case. So those are the 3 possibilities we have with power series. Okay. So this then forms the basis for the theorem that for this particular section. This is going to look redundant, but I'm just going to write this down here again. Theorem. So we're given a power series. Given a power series. And let's make it very general. Summation as n goes from 0 to infinity of some coefficient times x minus a raised to the n power. All right. So this is centered at a. There are 3 possibilities. Three possibilities. A, it converges only at x equals a. That's where it only converges at the one point. And that a is going to be what we have right here in our power series. That a there. The second possibility is that it converges for all x. And then the third possibility, which requires a little bit more work on our part, is this. There is a positive number R, we're going to call it capital R, such that the series converges if the absolute value of x minus that a is less than r. And then it diverges if the absolute value of x minus a is strictly bigger than the r. Now, this r is called the radius of convergence. So you're going to see some problems where they ask you to find the radius of convergence, and that is what we mean by the radius of convergence, okay, r. But let me also say this. In the first case here, if it only converges at a single value, though, we're going to say that the radius of convergence is equal to 0. And in the second case, if it converges for all values of x, we say the radius is equal to infinity. Okay. But in the third case, it's going to be some finite number. Okay. Now, for this last case here, for case C, we have to test the two endpoints of the interval. Test the two endpoints of the interval. All right. And then finally, one of this other definition, which I already pretty much gave you, is this. It's the definition of the interval of convergence. So I'm just write this again here. The interval, in quotes, the interval of convergence, end quote, is all the values of x for which the power series converges, okay, equals all the values of x for which the power series converges. Okay, all right. So with these kind of definitions involved, we're going to do a couple more examples here of this ratio test to see where these series converge. And when I did these problems at the back of the chapter, I found that this particular set of problems seemed to go pretty quickly. That's just was my experience with it. Because right away you know what you're going to be using that ratio test and going from there. So I hope that your experience is the same. Okay. So what we're going to do here is in general, we'll use the ratio test. In fact, I don't think I had a single problem there that I used the root test. I think it was all the ratio test. In general, we'll use the ratio test. Okay. Now, just as, again, a reminder here, the ratio test will fail at the two endpoints. We cannot, that's why we have to test the two endpoints separately. So, just as a reminder, the ratio test will be inconclusive, let's put it that way. Inconclusive at the two endpoints. Okay. All right, so let's look at another example then here. Summation Okay, let's say this is what the question's asking. Let's find the radius of convergence and let's find the interval of convergence. So find radius of convergence and the interval of convergence. Okay, so here's the series, n equals 0 to infinity of minus 3 to the n, x to the n, over the square root of n plus 1. All right. I think we can get part of this done, at least then we'll take a break. So we're going to use the ratio test. And so our a sub n is the minus 3 to the n, x to the n, over the square root of n plus 1. All right. Okay, just like with the other examples, we look at the quotient, a sub n plus 1 over a sub n, absolute value. All right. Every place there's an n, let's put an n plus 1. So we're going to have minus 3 raised to the n plus 1 times x raised to the n plus 1 over what? The square root of n plus 2. n plus 1 plus 1. n plus 2. And that'll be over the a sub n, which is minus 3 just to the n, x to the n, get that up higher, over n square root of n plus 1. Okay, so big ugly thing, which is going to rapidly get simpler. All right. Now again, for purposes of absolute value, let me point out this. Minus 3 raised to the n plus 1 power can be rewritten a little bit differently. Notice this minus 3 is really minus 1 times a positive 3, all raised to the n plus 1 power. So it can be rewritten as minus 1 to the n plus 1 power times positive 3 raised to the n plus 1 power. I'm just breaking it apart. It's really minus 1 times 3, and I'm just breaking it apart a little bit. And I can do the same thing, of course, with minus 3 to the n power. That's going to break apart as minus 1 to the n power times 3 to the n power. All right? So with that said, since I'm dealing with absolute value here, when I rewrite this thing for that minus 3 to the n plus 1, how could I just write that? Since we're talking strictly about positive values, but we're doing the absolute value.
Ignore the name one.
Just ignore the negative, and so I would write it as what, Will, for that top one?
Fraction?
Not just the first part of it, not the whole thing. How would I over here? How would I write that minus 3 to the n plus 1?
You just write it as 3 to the
N plus 1. Yeah, right. Yeah, we can just get rid of that minus in front of the 3 like that because we know we're just taking the absolute value. Okay. Now I still have to keep here the absolute value around the x to the n plus 1. So I still have to retain that. And then the square root of n plus 2, that's always going to be a positive number. So I don't have to keep the absolute value surrounding that. So I can rewrite the top part of it just like that. And then this is all over, well, the bottom part it also is just going to be 3 to the n power without the minus there. And I still need to keep the absolute value around the x to the n. And then again, that square root, I don't have to keep the absolute value around it anymore. So I've got that. And again, of course, that still looks pretty ugly, but when we flip the bottom part around, it simplifies quickly. So we have 3 to the n plus 1 times that absolute value of x to the n plus 1 over that square root of n plus 2, and then we multiply it by the reciprocal of the bottom. So that's going to, now we're going to have on top the square root of n plus 1 over 3 to the n power times the absolute value of x to the n, like that. All right. Okay. And then we see that a couple of things are going to be reducing or canceling each other out. Let's say reducing each other. So let's look at the 3's there. What am I going to be left with? I got a 3 to the n plus 1 on top and a 3 to the n on the bottom. So when the dust settles, what am I left with? 3 to the 1 on top, right? So I still have a 3 left in the numerator. Now let's look at the x's. I've got an x to the n plus 1 on top and an x to the n on the bottom. So I'm going to be left with just an x on the top. And it's still going to be absolute value. I'm not going to be dropping that. Okay. And then this is being, and then let's see, we still have that square root of n plus 1. I'll put that kind of separately here as another fraction. That's on top, and on the bottom we have the square root of n plus 2. All right. So this is our quotient, and then what we want to do then is take the limit as that n goes to infinity. So we're looking at the limit as n goes to infinity of what? 3 times the absolute value of x times that square root of n plus 1 over the square root of n plus 2. All right. Well, what's that last fraction going to have as a limit when n gets bigger, bigger, bigger? It's going to be 1. Let's go through that. Okay, we need to divide everything on top and bottom by the same power of n. Okay, so what about if I divide under the radical, I divide everything by n. So I have n over n plus 1 over n under that top radical, and I have to do the same thing to the bottom. N over n plus 2 over n and the bottom radical. And then we can see that the second term in both of these radicals goes to 0, but the first term is n over n, which is 1. So the limit is equal to 1 here for that fraction. Okay, that's 1. So my limit here then is equal to 3 times the absolute value of x times 1, or just 3 times the absolute value of x. All right. And then for the ratio test, for convergence, we want this limit to be less than 1. So we need to then solve for 3 times the absolute value of x less than 1. So what's the first step I need to do to solve this inequality? Very first step. Well, okay, either would work. I would divide by 3 first, but Jenna, what you're saying will also work. Let's divide by 3. So we have the absolute value of x less than 1/3. Now what you're saying, though, would also work if you're careful. So what you're suggesting is put minus 1 less than the 3 times the square root of x, and so squeeze it between the two ones like that. And that's okay. In your case, though, what would you then do next? Oh, wait a minute. Oh, I don't need that absolute value in there anymore. I just need an x. And divide everything by 3. So if I divide everything by 3, I get minus 1/3 less than x less than a positive 1/3. And that's the same thing we get with the other method here. We have the absolute value of x less than 1/3, which means that the x is squeezed between positive 1/3 and negative 1/3. So we then can write this as without the absolute value, x less than 1/3, but greater than the negative 1/3. All right. So this, we know between those two values, it converges. So it converges here. But after we'll take a break, but what we have to do next is we have to find out what does it do at these two endpoints. Oh, before we do that, we can answer the first question. Remember, we had two questions up here. Find the radius of convergence and the interval of convergence. We found that the absolute value of x has to be less than 1/3. So what would our radius of convergence be? It would be the 1/3. That value right here, that is our r, the radius of convergence. So r equals 1/3 radius of convergence. So we can answer that one. So let's take a 5-minute break and then we'll test the two endpoints. Oh, yes, sir.
Explain real quick how you know that this is less than 1. I understand why the one right there is equal.
Okay, right. Okay, the thing is, what we're trying to find out, this is what we're trying to find out. We're trying to find out where this whole series converges. Okay, we're using the ratio test. So we're getting that quotient and we're simplifying it, and we're finding out, well, what is its limit as n goes to infinity? So the limit of, we simplified it to this, so we want to find out what's the limit as n goes to infinity, and we know that this limit is equal to 1. So this will go to a 1, and this still stays 3, and that still stays the square root, the absolute value of x. So that's the limit of our ratio is 3 times the square root of x. Look at this.
So the limit of n goes to infinity is 3 absolute value.
Yeah, times the square root. Absolute value of x. Now, we want this to converge. We want to find out where it converges. So by the ratio test, it has to be less than 1.
You choose infinity.
Yes, right, because we want to find out where it converges for sure. So that's why we're setting it less than 1 and then proceeding to solve that inequality. Okay? All right, sure. Well, if you have it, there's some things up there, Kyle. You're not doing. Oh, I'm sorry. You look a little pale. Yeah. Into a doctor? Well, you don't have to tell me, but maybe you might want to see one if you're not getting better. Just a hint.
He was sitting at the master this morning when I was there. He's like, can you help me? And then I was like, yeah, come over here. And then I started talking, like, maybe I don't want you to sit back.
No. You're okay? You have hands, but what about covering the mouth?
Use my shirt.
Whatever.
I'm trying my best not to get anyone sick, because I don't want anyone to have that.
So we're gonna win the ball game tonight?
I wish. It'd be fun.
Yeah, it would be nice.
Going to the Blues game then?
They're going to this game tonight. Pitcher's sick.
Yeah, it's fine. I'll sleep until.
Okay. Somehow you just aren't quite as sick when you're doing something like that. But coming here, it's like, oh my gosh, I'm sick.
It takes too long to medically kick in.
Well, yeah, antibiotics, if that's what you're talking about. Yeah, they do take a while.
If I take biotics, I have to keep taking them until they go.
That's what they say.
Very forgetful.
Yeah. You hope you get something where maybe you can only take it at most twice a day.
But it's like 3 times.
3 times a day. Once you get to 3 times a day, you're in trouble. You can be in trouble. And 4 times a day, forget it.
I don't even like. It's not even with meals. That's
Yeah. I don't know.
So is like 11.9 and 10 really long?
11.9 isn't too bad. I haven't prepped 11.10. I'm going to be prepping this weekend, so I'm going to try to keep it as short and sweet as possible. All right, we'll see. I can't make any promises yet.
I was looking at it and it looks.
11.9 is basically one concept.
Added to what we were doing.
Well, it's actually something we've already seen, but we're focusing more on it. So in a way, it's not new, but it's not bad. This is a long chapter, though, 10 sections, so which is good. Okay, well, let's continue here then. So anyway, so we've gotten this series. We've determined that the radius of convergence is 1/3. So let's write up here what we've got here. So we've determined that from -1/3 to +1/3, it converges. And R, the radius of convergence, is equal to 1/3. All right. So let's then, what we have to do next is test the endpoints. Test the 2 endpoints. Because it could be on one or the other of them, or even both of them, or maybe neither of them, it converges. So let's look at -1/3 first of all. All right, so our original series here is -3 to the n, x to the n over square root of n plus 1. So we're going to plug in -1/3 here for the x. So we're going to have summation n equals 0 to infinity, -3 to the n. Now for the x here, let me use a little parentheses. I'm going to put in a -1/3, close the parentheses, and I have to raise that to the n power. And then that's all over the square root of n plus 1. All right, so I think we can do some simplifying here of the top part. Let's look here at this top part here, this whole thing here. Let me go down here and just kind of look at this. -3 to the n times -3 to the n. Well, they're both being raised to the same power. So I can multiply them in one parentheses and raise them to the n power. So I can take the -3 times the -1/3 all in a single parentheses and raise that to the n power. Okay. Now -3 times -1/3 is what? 1.
So this is 1 raised to the n power. Well, no matter what n is, this is going to equal 1. So that whole messy part in the numerator simplifies to just the number 1. So we now have this, the summation as n goes from 0 to infinity of 1 over the square root of n plus 1. Okay. All right. So the question is, does this converge or diverge? And why? Okay. Yeah, that's basically it. We can do there's a couple of tests we can do. One of them is we can just do a limit comparison test with the p-series 1 over the square root of n as n goes from 1 to infinity. Or another thing we can do with this is we can actually recognize that this is really the exact same thing as this. It actually equals this. Notice here when n is equal to 0, it starts out as over the square root of 1, and then it goes to n equals 1. Here, let me just write it out. It's 1 over the square root of 1 plus, now n is equal to 1. It's 1 over the square root of 2. Then n is equal to 2. It's 1 over the square root of 3, etc., like that, if we just write out a few terms. And that's exactly the same as our p-series. This is also 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3. In fact, we don't even have to do a limit comparison test because it is, as Jenna says, it is a p-series. So it's a p-series with p equal to what number? 1/2. So p is equal to 1/2. So it does diverge. Okay. So therefore, at -1/3, it diverges. Now let's look at the other endpoint. Let's look at +1/3. Okay, and we're going to plug that in again to our original series here. So that's going to give us the summation n equals 0 to infinity -3 to the n. Now in place of the x, I put 1 +1/3 raised to the n power, and it all goes over the square root of n plus 1. Okay, so now we have this one, and again, let's simplify the stuff in the numerator here. This is going to be -3. Let's just write this up here. Let's go down here. -3 to the n times 1 over 3 to the n is going to be the same as -3 times 1/3, all raised to the n. And in the parentheses, it's -1. So this becomes the summation n equals 0 to infinity of -1 raised to the n power over the square root of n plus 1. Okay, now what kind of series do we have? An alternating series. Will it converge or diverge by the alternating series test? First of all, is 1 over n? 1 over the square root of n plus 1, is it decreasing? Yep. As n gets bigger and bigger, the denominator gets bigger and bigger, so it gets smaller and smaller. So that's the first thing we have to look at. And then the second thing with the alternating series test, as n goes to infinity, is 1 over the square root of n plus 1, ending up equaling to 0. And the answer is yes, it is. So therefore, I can say that this series converges by the alternating series test, AST. All right, so we find that one endpoint converges, the other one doesn't. So the second question was the interval of convergence. And so let's see, we found that at negative 1/3, it diverges. So we're going to put parentheses around negative 1/3, comma, but we found that at positive 1/3, it converges. So we're going to use a bracket there. And that's our interval of convergence. That's how these problems run. So I want to do one more here, just to, again, just get this idea down here. And then that'll be it for this particular section then, right? It's basically just a couple of concepts here. It's all about this, using this ratio test. Okay, so last example for this section, summation n equals 0 to infinity of n times x plus 2 to the nth power over 3 to the n plus 1. Right. Okay. So again, our a sub n term is n times x plus 2 to the nth power over 3 to the n plus 1, and we're going to use the ratio test. Okay. All right, let's get our quotient, absolute value of a sub n plus 1 over a sub n. So n is going to be replaced by n plus 1. I'm going to use parentheses. Then x plus 2 to the nth power is going to be replaced by x plus 2 to the n plus 1. And then that's over 3, what is it, to the n plus 1. So that's going to be 3 to the n plus 2 power. And that's all over n times x plus 2 to the nth power, all over 3 to the nth power. Plus 1, sorry, plus 1. All right. Okay. Now, most of this stuff, we don't need to keep the absolute values around. 3 to the raised to a power is going to be positive. N plus 1 and n are both going to be positive. So I'm going to have n plus 1 in parentheses. Now, I do have to keep the absolute value around x plus 2 raised to the n plus 1. Need that still. Over 3 to the n plus 2. I don't need absolute value there. And then it's over n. Now, again, I need absolute value. X plus 2 raised to the n. Need the absolute value there. And then that is over 3 to the n plus 1. All right. And then we can simplify this mess in the next step. So we had carry over our n plus 1 times the absolute value of x plus 2 to the n plus 1, all over 3 to the n plus 2, and then we multiply it by the reciprocal of the bottom. So that's going to be on the top now, 3 to the n plus 1 over n times the absolute value of x plus 2 raised to the nth power. Right. Okay. And then things are going to cancel out here or reduce also. So in this case now we have what? We have, how are the 3's going to reduce? What was that now? 3? 3 on the top and 3 squared on the bottom. Okay, well, okay, 3 on the top and 3 squared on the bottom. Now, how can that simplify? That still can simplify. Well, yeah, 1 on top and a 3 on the bottom. So basically, the 3 simplify out to a 1 on top and a 3 on the bottom. All right? Okay. Now, let's look at the x plus 2 powers. What's going to be left where with the x plus 2 powers? Yeah, x plus 2 on the top, we're still going to have a power of 1 there. So we have to keep that absolute value, x plus 2 to the first, or we could even say to the first power, is still going to remain on the top. And then we still have that, let's also then separately write, still got an n plus 1 on the top and an n on the bottom. All right. So you should be able to see the pattern here of what's happening. That last fraction, as n gets bigger and bigger, is going to go to 1. All right? So let's now take the limit of this as n gets bigger and bigger of 1/3 times the absolute value. It's just x plus 2 times n plus 1 over n. And this last one's just going to go to a number 1. So my limit is 1/3 times the absolute value of the x plus 2. Okay. So I'm wanting to find out where this converges. So with the ratio test, when I set this less than 1, it's going to give me the values where it converges. Okay. Now, so this is something I need to solve. What might we want to do, first of all, to help start to solve that inequality there? Yeah, that's the best thing to do. Let's multiply by 3. So I have absolute value of x plus 2 is less than 1 times 3, or 3. And then that is going to be my radius of convergence here. That's 3. All right. Okay. Now let's squeeze that x plus 2 between plus 3 and minus 3. So we can drop the absolute values, make it less than 3, yet greater than negative 3. And then subtract 2 from all 3 parts of it. Minus 2, and minus 2. All right. So on the left side, we end up with what? Negative 5, minus 3, minus 2, less than x, less than 3 minus 2 is 1. So any value of x between minus 5 and 1, we know it'll converge. Okay, so again, we have to look what's happening at each of the 2 endpoints. So let's start out, first of all, with minus 5. Doesn't matter, but we'll start out with that one. So let's check minus 5. All right, so again, we have to go back here to our original series here and plug that in. All right, so our original series is here. So let's plug in minus 5. So we get the summation, n equals 0 to infinity of n. Now we plug in a minus 5 in there for the x, so we're going to get minus 5 plus 2. So in the parentheses, we're going to be left with a minus 3 raised to the n power over 3 to the n plus 1 power. Okay. So that's what we're going to see, what in the world is going to happen here with this one. Okay. So let's look at how can we simplify that part of this thing so we have something a little bit easier to deal with here. Any ideas? Yeah. Okay, that's one thing we can start with. Absolutely. So Art's recommending let's make that minus 3 to the n power. Let's break it up in 2. at two parts as minus 1 to the n times positive 3 to the n. So let's do that. N equals 0 to infinity of n now times minus 1 to the n times a positive 3 to the n. And then that's all over 3 to the n plus 1. Okay, so that's a real good start. Then there's something else that we can still reduce here with this thing now that we see it like this. Right, so what am I left with then when I cancel out the powers of 3 that I can cancel out? Okay, did you say negative n to the n? Is that what you said? Well, now how would you get negative n? Okay, wait a minute. Are you saying, negative, wait a minute. Negative 1 to the n times n, and then what do we have? Over 3? Okay, all right. Yeah, no, wait a minute. Can it just be negative n to the n? Over 3. Okay. All right, what about that? Thoughts from anyone on whether or not we can just make it look like that? Why not?
Because then the n.
Right, then the n is being raised to a power. Notice that in what we have here, this n here, it's just staying to the first power. So what you're trying to do is you're forcing it into something that it's not, because by doing this, this is minus 1 to the n times n to the n when you do it that way. And that's not what we have. So you can't do that. No? All right. Okay, so this is as much as we were able to simplify this thing by. All right. Okay, and the whole point of this, what we're trying to figure out, does this converge or does it diverge? And this is as n goes from 0 to infinity. So that n, as each one of those successive terms, that n keeps getting bigger and bigger. But sometimes we're multiplying it by 1, other times sometimes we're multiplying it by a negative 1/3, other times we're multiplying it by a positive 1/3. What was that? It doesn't, it diverges. But let's get the reason why it diverges.
Because the limit doesn't exist?
Right. It's through the divergence test. Divergence test. Okay, if we have, this is what that says, if we have the sum of something, as n goes from 0 to infinity, and we look at this term here, and we take its limit as n keeps getting bigger and bigger, if that limit either is not equal to 0 or does not exist, if it doesn't equal 0 or does not exist, then it diverges by this test. Then the series diverges by this test. So this thing is actually, this goes between big negative numbers and big positive numbers, all right? When n is equal to 1,000, we have 1 times 1,000 over 3. When it's equal to 1,001, that's an odd number. It's equal to minus 1 times 1,001 over 3. And then it just keeps going like that. We just keep getting to bigger numbers over here, bigger numbers over here. It doesn't have a limit. So the limit doesn't exist. So that, it diverges by the divergence test. Okay?
That seem reasonable?
That's something that you should get in the habit of eyeballing. Does this thing look like it's going to be getting small to 0 when we're just looking at the term? Not the summation, just the term, as n gets bigger and bigger. And of course it doesn't here. So therefore we know it diverges. So therefore it diverges. So therefore x equals -5 is not going to be in our interval of convergence. Now let's test the other endpoint, which was what? What was the other endpoint? Was it 1? Do with this, right? Okay. All right, let's check 1. Check x equal 1. All right, so now we're going to plug that into our original series here. So here we're going to plug in x equals 1. So we have here we go. We have the summation of n equals 0 to infinity of n. Now here we're going to plug in a 1, so that's going to be 1 plus 2. That gives us a 3 raised to the n power over 3 to the n plus 1. So that's what we get by plugging in the other endpoint. Okay. So again, let's simplify this term here. And what does the what does this part here simplify to, this whole thing here?
Number 3.
Yeah. So n equals 0 to infinity. We still have an extra power of 3 on the bottom. So we're left with n over 3. All right. Now, again, divergence test. We look at this thing here, right here. As n gets bigger and bigger, it's not flipping back and forth, but it's getting bigger and bigger and bigger. So its limit does not equal 0. Since the limit as n goes to infinity of n over 3 does not equal 0, in fact it equals infinity, it diverges again by the divergence test. Okay. So therefore, in this case, both of the endpoints failed. So my answer then is -5, 1, but I have parentheses on both of them because both endpoints failed. And then this then is my interval of convergence. Okay. Just one thing, this is something that's connected with the homework that I think before we break for the weekend here, let's see, testing 7.8, yeah. Let me find this thing. Here it is. Okay. Just something I want to point out that's a little bit different here from the homework for this section. 11.8. This is number 20. And when you do number 20, what you come up with here, once you do all your simplifying and everything, is that you come up with the absolute value of 2x minus 1 has to be less than 5. All right. So this is what you get. Well, actually, what you initially come up with is this: is that the absolute value of 2x minus 1 divided by 5 has to be less than 1. And so what I'm doing, this is from using the ratio test. And then what I'm doing for the next step is just multiplying by 5 to get that the absolute value of 2x minus 1 has to be less than 5. Now, with this thing, you might say, oh, yeah, that's my radius of convergence, 5. And that's not the case. No. The reason it's not the case is because we have a 2 times x right here. Okay. The radius of convergence for this is going to be 5 over 2 is going to be the radius of convergence.
What about the negative 1?
Yeah, So let's actually look at this thing. Let's solve this inequality. So we have the absolute value of 2x minus 1 has to be less than 5. That means that we can take away the absolute value signs and that the 2x minus 1 has to be squeezed between plus 5 and negative 5. All right? And then we add 1 to all 3 parts of it. Add 1, add 1, add 1. And we get, let's see, minus 5 plus 1 is minus 4 is less than just 2x. And that's less than 5 plus 1 is 6. All right? And then we finally divide by 2. So we get minus 2 is less than x is less than 3. All right? Now, notice that between minus 2 and 3, we have 5 units of distance. Right? 5 units of distance. Between negative 2 and the positive 3. So radius, just like radius of a circle, is half the diameter. So that whole distance between the 2 endpoints is 5. So the radius is going to be half of that. So the radius is really half of this, 1/2 of the 5, which is 5 over 2, not the 5 that you might jump to the conclusion that it is, okay? And then, of course, for this particular problem, then, you're going to test the negative 2, you're going to test the positive 3 to see whether they converge at whether the series converges at either of those 2 endpoints, okay? All right. Okay, I think you've got enough tools there that you can be able to handle the homework there for this section, all right? And so next time, then, we're going to go on. We're going to do 11.9. And so between all the classes next week, we'll be covering 11.9 and 11.10, all right, everything we need for the test. So, you know how it is before a test, it seems like there's all kinds of work involved. I'll try to keep the take-home quiz to be a reasonable length, so I might even make it a little bit shorter than the last one. But I want to get certain types of problems in there for you guys to have as practice, okay? So you'll be getting those on Monday, and so don't look so unhappy about this, Cassandra. You will survive this. All right, so have a great weekend, and I'll see you guys on Monday then.